Hey everyone, welcome to a new series on Kaggle projects. In this series, we'll be looking at various Kaggle projects and see how different people have attempted them. Today's project is Titanic Machine Learning from Disaster. Before we begin, let's look at some background about this project. On April 15, 1912, during her maiden voyage, the widely considered unsinkable RMS Titanic sank after colliding with an iceberg. Unfortunately, there weren't enough lifeboats for everyone on board, resulting in the death of 1,502 out of 2,224 passengers. That's around 70% of the passengers and crew that couldn't survive. Now, the challenge, as you might have guessed it, is predicting whether a person survives the crash or not. Now, in this competition, Kaggle gives us two data sets. One is called a train set and one is a test set. Both of these have passenger-related information such as their age, gender, socioeconomic class, etc. Now, the train set also has something called the ground truth. Basically tells you whether the passenger survived or not. Now, using this train data, we have to explore the data, find trends, build a machine learning model, and hopefully predict in the test set who survives and who doesn't. Now, before we dive in, I think it's a good time right now to give you guys a brief background about machine learning and how we data scientists approach such problems. So artificial intelligence has existed for quite some time right now. In the early 1900s, it was more of rule-based programming, where you would write a code that if this thing happens, then execute this, else do this. A simple example that you can take is that of spam detection. If you wanted to detect spam, you could write some code that if you see certain letters, mark it as spam, otherwise it's a good email that can go through. Now you can quickly see how this strategy would fail. As the spammers got more intelligent, they quickly broke through such rules. Then came machine learning. Now, instead of creating rules and hard coding their values, we created machines or mathematical models that would learn from the data. Once they have learned enough, they were able to see patterns in the data and use this model to predict on data that it hasn't seen before. Now, in recent years, there has also been development on deep learning, a different kind of model that uses neural networks, but more on that later in some other video. Now, machine learning is a broad term, and you will hear many models out there, but they can all be grouped under three main categories: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is when you have a data set which has a bunch of input columns and an output column. Then you train your model that whenever you see these kind of inputs, you have to predict this kind of output. This kind of case where you have input and output, or more specifically labeled data, is a case of supervised learning. Now, depending on what you want to predict, if it's a numerical value, then it's a case of regression, supervised learning. And if it is classes or categories, then it's a case of classification, supervised learning. In our case, since we want to predict whether a passenger survives or not, this is a case of classification, supervised learning. Now that we have an idea about machine learning, there's just one more thing I need to tell you guys about. When we have a data set, it has a certain number of columns. These are called the dimensions of a data set. The input columns that we spoke about is also referred by other names. They are also called features of a data set. They're also called the predictors because they help in making the prediction. And in machine learning, they're also referred to as the letter X. The output column also goes by the name of label, and that's why that name, the label data set, comes in. It is also called the target column or also the letter Y. Now, there is a specific way how data scientists approach these kind of problems. It's called a machine learning pipeline. This is how a machine learning pipeline looks like, and we will be visiting this infographic again and again. The first stage in the machine learning pipeline is the problem definition. Here, we define what problem are we trying to solve, and then we try to come up with an idea as to how we will solve it. This part is already taken care of by Kaggle. They have told us that we need to create a machine learning model that will predict whether a passenger survives or not. Hence, this is a classification supervised learning model. The next step in the machine learning pipeline is data collection. Data is not always readily available, but in this case, luckily it is. Kaggle provides us with this data, so we can proceed from this step also. The third step is the exploratory data analysis. Once we have our data, we explore the data for its data quality and also to find different trends. So let's see the EDA for this project. In this notebook, the author uses a very methodical approach and he goes through all the stages step by step. The very first step in any data science journey is the exploratory data analysis. After loading the data, it is very important to have a glance at the data, and for that, the .head function is really useful. Once we look at the data, we find that there are various kinds of data types in the data set. The author identifies 3 different types of data types. There's categorical features, numerical features, and mixed data types. Categorical features are basically qualitative features, and they can be nominal, ordinal, ratio, or interval based. Knowing the data types is a very important step. It helps you decide what kind of visualizations, functions, and even transformations would you use for your machine learning model. In this data set, there are 4 categorical features: survived, sexed, embarked, and P-class. And P-class is also an ordinal feature, so basically the order of the numbers matter. Numerical features can be of 2 types. They can be discrete or they could be continuous. In this data set, we have 2 continuous features, age and fair, and we have 2 discrete features, SIB-SP, the number of siblings and spouses, and PARCH, which is the number of parent and children. The only remaining feature is the ticket feature, and that is identified as an alphanumeric, so basically a mixed data type. The next important step is to see if there are any missing values in our data set, and this can be easily found using the .info function. Here, the author identified that cabin, age, and embarked are features that contain missing values in the training data set, whereas the cabin and age are incomplete in the testing data set. Now that we know the data types and missing values, it's important to see how each of these features are distributed. This can be done using the .describe function. When we use the .describe function, we get the 5-point summary: the mean, the standard deviation, minimum, maximum, and the quartile values. From this, the author derives some very valuable insights. For example, there are total 891 records, which is actually 40% of the actual number of passengers on board the Titanic. The survived is a categorical feature, which has the value 0 or 1. The survival rate is around 38%, which is quite representative of the actual survival rate of 32%. More than 75% of passengers did not travel with any parent or child, and nearly 30% of passengers had siblings and or spouse aboard. Varied significantly, with few passengers paying as high as $512. Also, on board the Titanic were few elderly passengers within the range of 65 to 80 years. The .describe function can also be used for objects by including the syntax include equals O. From this, the author finds these insights. The names are unique across the data set, so there are no duplicates in names. The sex variable has 2 possible values, and the males are 65%. Cabin value has several duplicates across samples. Alternatively, several samples could have shared a cabin. Embarked takes 3 possible values. The port S has the most passengers of 644. The ticket feature has a high ratio, around 22% of duplicate values. This could also indicate that several family members shared the same ticket. Another very important part of the EDA is visualization, and this notebook does a great job at it. For example, we see here that more than half the passengers were males, and their survival rate was very low, whereas less than 100 females did not survive, and majority females survived. Hence, the survival rate for women on the ship is around 75%, while that of men around the ship is 18 to 19%. Hence, we can say that sex is one of the important features in predicting the survival rate. If we look at the ticket class, we see that the first class had majority survivors. whereas the third class had a huge majority of people who couldn't survive. As a result, the P class 1 survival rate is 63%, the P class 2 survival rate is around 48%, and the P class 3 was just a meagerly 25%. Again, this feature looks also very important in predicting the survival. So we saw that the sex and the P class has an important role in predicting the survival rate. How about the port of embarkation? We can use a count plot to see a categorical value and see how many people survived based on which port they embarked upon. We see here that the majority people embarked on port S. Unfortunately, majority of them did not survive. Port C was lucky and the survival rate is higher in port C. If we break it down further, we see that the majority of the passengers in port S were from P class. Now, it would be interesting to see how the three features combined, sex, P class, and embarked, all three impacted the survival rate. And this notebook does just that. In this plot, we have all of those three categories we discussed earlier. We have the sex colored as green and blue. We have the port of embarkation, so each plot represents one port, and the x-axis represents the class. The first thing that we see here is that in port S and Q, the female survival rate was higher than the male survival rate. However, at port C, the male survival rate is higher than the female survival rate. And this is something really strange. Once we are done with the EDA, the next step would be to take care of the missing values. Now, depending on the importance of the features with relation to the target variable, we can choose to fill the missing values, replace them, or get better data. Most of the notebooks choose to fill the missing value of age in very smart ways. As you can see in this heat map, the age is heavily correlated with the P class, the parent and children, and the sibling and the spouse. So most of these notebooks, they have done a grouping based on these three features and then found the median age. Using that median age, they have used it to fill the missing values. For the missing value in Embark, the mode can be used. The next step towards the model building is feature engineering. Feature engineering is the process of creating new features from existing features, and in most cases, this adds value to your model. In this notebook, the author does a great job at creating new features. A unique name value does not add much to the machine learning model. One of the targets of the feature engineering is to find some commonalities, to create groupings that helps us predict the outcome. One way to do this is to extract the title from the names. There are 17 titles in the data set. Most of them are very rare and they can be grouped into a rare category. The final outcome looks something like this, where there's a title for children, a title for women, a title for men, and then there are some other titles. Again, looking at how this new feature relates with the target variable, when we look at the survival probability, it shows us that the survival rate for the female title is the highest, followed by that of children, and followed by that of men. The next important feature that many of these notebooks have created is the family size. Instead of looking at two features separately, the sibling and the spouse and the parent and the child, it's also better to combine both of them together. By just taking a sum, we create a new feature called family size. Again, looking at how this new feature relates with the final outcome, we can see that the survival probability of a single person is very low, and the survival probability of a small and medium family is quite high. When it comes to the cabin feature, some notebooks have decided to drop this feature because of the huge amount of missing values. In this notebook, the author chooses to replace the missing value with a new cabin type called X. As we discussed earlier, the ticket feature is an alphanumeric feature. It contains string and numbers. One way to take care of that was to just extract the prefix of the ticket, and then anywhere where there is no prefix, we'll just replace it with an X. Another interesting feature that many of these notebooks have created, in addition to the family size, is alone feature. So if that person is traveling alone and the family size is just 1, then the is alone feature has a value of 1 and it has 0 everywhere else. As we will see later on, this is alone feature is also a very strong feature that is heavily correlated with the target variable. After feature engineering, it is important to do encoding. And the process of encoding is changing categorical values to numeric values. Now, different notebooks have taken different approaches. When the categories are not large, they have simply mapped the categories to numbers. And when the categories are large, then they have used various kinds of encoding schemes like label encoding, one-hot encoding, etc. Once the encoding is done, our data would look something like this, where there are no more text values remaining and everything is now numbers. Remember, a machine learning model can only take numbers as its input, and that's why the process of encoding is really important. Another important technique that people have used is to create bins or ranges. Instead of keeping so many different ages, it is easier to create age groups and label those groups as numbers. Once we have encoded all our features and everything is numeric, then we can run a correlation plot and then see the significance of all of these features with relation to the survived target variable. As you can see here, the survived target variable has the highest correlation with sex, then P class, then the fair, and then the is alone feature. Now we can also see from here that there are features which are heavily correlated to each other. So we can choose to select only the one which has the high significance to survive and perhaps drop the other ones. Now, if our data is spread on different scales, then perhaps there is also a requirement of feature scaling. Now, not many notebooks have done this, but in this case, the author chooses to do feature scaling using the standard scaler. As you can see here, after scaling, all the values are now within a smaller range compared to before. One way to approach the problem is to use one of the basic classification models out there. Some of the famous ones are logistic regression, k-nearest neighbors, support vector machines, decision trees. As seen in this notebook, the decision tree gave the best performance out of the base classifiers. Now, another technique that can be used in machine learning is to use ensemble methods. Random forest is one such ensemble method where it takes several weak learners, typically decision trees, and makes a better prediction out of them. As highlighted in this notebook, decision trees suffer from overfitting. When we are using ensemble methods like random forest, we avoid the issue of overfitting. This notebook does a great job of modeling the data and also explaining how we can build a good classification model. As highlighted here, there are multiple ways to evaluate a classification model. Remember that the metrics for evaluating a classification model is different than the metrics used for a regression model, for example. We can use the confusion matrix, receiver operating curve, or also called the ROC curve, and also we can use something called the area under curve. Some other basic metrics include precision, recall, accuracy. These are all the metrics that are used for comparing classification models. The author also uses different techniques like cross-validation and grid search. Usually cross-validation is used to compare different models and choose one, whereas grid search is used for hyperparameter tuning. A general observation amongst all of these notebooks is that boosting tends to work better for this problem than the bagging ensemble method. This is another great machine learning technique. What it does is it runs machine learning models and then votes their outcome and then chooses a best one. In this notebook, the author uses another variant of machine learning techniques. He uses ensembling and stacking models. In his first level of models, he generates the outcomes using these classifiers. Finally, for the second level of learning, he uses an ensemble technique called XGBoost and has great results from it. Once you have built the machine learning model and are happy with your predictions, we can also look at the feature importance. One such notebook found that the highest feature that contributed to the predictions was the is alone feature that was feature engineered. Also, sex and P class and family size had importance. Also, as shown in this notebook, the features need not be the same across all models. Some models will give more weightage to some features, while other models give more weightage to other ones. For example, here we see that the fair is the highest importance in these two models, but we see similar features coming on the top. So in general, we can say that the age, the fair, and the sex contributed the most towards the model prediction. To summarize, we saw how we can use data science to find trends in our data, how we can use feature engineering to create better features that will then help us in our model prediction, and how we can use classification-based models and other advanced ensemble techniques to get better predictions from our machine learning models. So that summarizes the Titanic project on Kaggle. I hope you liked it. If there's any other project you want me to review, let me know in the comments below. And thank you for watching.